Good morning. Welcome to our webinar for the 2016 Consolidated Innovative Nuclear Research FOA, which we are commencing at this time. My name is John Gilligan. I'm director of the DOE NEUP Integration Office in Idaho. I just wanted to welcome you again this morning from Germantown, Maryland. We have a large audience here in the studio, but I wanted to recognize a couple of additional staff members that I failed to recognize yesterday. One is Joanna Serra, who's also here with us that you may interact with in the future, and also Derek Ogg, who has been with us for the last couple of years and supportive of the DOE program here in Germantown. So thank you very much for your efforts. We will continue today with the presentations from the various parts of the program. This is a very large program, of course. When we say integrated, it's integrating both NEUP along with the NEAT program and NSUF. And fortunately, today we have Dan Ogden, who's the Deputy Director of NSUF, to kick things off and explain the NSUF program in great detail. And so Dan, I'll ask you to do that right now. Thank you for being with us.
Thank you, John. Thank you. As John mentioned, I'm the Deputy Director of the NSUF. We have about 90 minutes today to talk about NSUF and the associated work scopes. So I'll start off with talking about the changes that are important from last year for this FOA. We'll follow that with an overview of NSUF, a little discussion about requesting NSUF access. It's a little different if you haven't been involved in that before. An important change from last year is a consolidation of NSUF access to 2 work scopes. We'll talk about that a little bit. That'll take about the first 30 minutes if we stay on track, and then we'll use the rest of the 60 minutes to address the various work scopes that are associated with NSUF. So I would ask, if you have questions as we're going along, it would be best to submit those during the sections that we're in. We will be switching speakers, so it'll be easier to address that while we have the appropriate speaker up here on the mic. Okay, important changes from last year. First thing, if you didn't notice, we have changed our name to match our evolution. We're no longer known as the ATR National Scientific User Facility. We changed our name to the Nuclear Science User Facilities to better represent the program and its scope. NSUF access has been consolidated to 2 work scopes. I'm going to talk about that in a little more detail farther on, but I want to mention that now. It's important if you're planning to request NSUF access. Please stay tuned for some details there. Another change from last year, uninvited applications will not be reviewed for NSUF access. NSUF resources need to be carefully managed in the time between invitations and submittal of full applications to complete the feasibility review, and we're not able to manage the uninvited applications during that time frame, so they will not be reviewed. We've added an option to the FOA, reserving the right basically to decouple an R&D request from an NSUF access request and evaluate and fund either portion if it's feasible. So that is applicable only in the NEAT NSUF1 work scope. Another big change for NSUF this year, we are offering high performance computing capability access through our program. So I'll talk a little bit more about that later. So that's a major new capability that's available. We are asking this year for applicants to provide the source, the scope, and the duration of their R&D support if they're requesting NSUF access only. This is to make sure there's no confusion after an award on the R&D support. So this lets us see what is there for applicants that are requesting NSUF access only. And also, very importantly, the schedule this year is slightly accelerated from yesterday, or from last year. I know this was discussed yesterday, but just as a reminder, the letter of intent, which is mandatory for NSUF, is due on August 27th, so that will come up very quickly. Pre-apps are due on September 17th, but you don't want to miss the LOI submittal date if you need NSUF access. Okay, user facility. I'm not going to spend much time on this slide. Hopefully most people out there know what a user facility is, but it's a tremendous opportunity for researchers to get no cost access to our DOE facilities. I'm going to focus a little bit more on what NSUF has to offer. So from the standpoint of neutron irradiation, within our suite we have the Advanced Test Reactor at the INL, High Flux Isotope Reactor at Oak Ridge, we have the ATR Critical Facility at the INL, the NRAD Reactor at the INL, the reactor at MIT, and the Pulsar Reactor at North Carolina State. All of those are available through the NSUF program. We also have ion beam capability available through the University of Michigan and the University of Wisconsin. We have synchrotron irradiation available at APS, at the Advanced Photon Source. This is through the Illinois Institute of Technology, the MRCAT beamline. We have a lot of hot cell capabilities available through NSUF, HFEF at INL. We have hot cell capabilities at Oak Ridge, MIT, up at PNNL, and also available through Westinghouse, one of our industry partners. Post-irradiation examination, there's a tremendous amount of instrumentation available through the NSUF. This is just a little sampling that's on this slide. We have a lot of capability at the INL, of course, at the Center for Advanced Energy Studies, which is associated with the INL in Idaho Falls, capabilities at many of the universities associated with NSUF, also down at Oak Ridge and up at PNNL. So it's a very large capability for PIE that's available. The best way to understand all those capabilities is to visit our website, nsuf.inl.gov. We also have available a sample library. This is a cache of irradiated material that has a pedigree. So it comes with an understanding of what the material composition was, what temperature it was irradiated at, what dose. This provides an opportunity for researchers perhaps to avoid an irradiation part of their research if we have the material already available. The irradiation portion of a project can take several years. It's important to take a look and see what we have in the library before you write your proposal. We may already have material of interest that could save quite a bit of time and expense in the overall scheme. Okay, high performance computing. We have two types of MOOS activities in Idaho, but most folks today are probably not interested in the one pictured here, but perhaps multi-physics object-oriented simulation environment. So with the addition of high performance computing capability to the NSUF, we have capability with our Falcon computer at the INL. Currently is in about the top 100 of supercomputing capabilities. What comes with this is not only access to the computer, but the INL has a lot of computational expertise that we can make available to support a research project. So this is an exciting addition to the NSUF, and it's a new opportunity for folks to take advantage of this capability. The NSUF also offers a lot of technical expertise. We don't just bring the researchers in, sit you next to a complicated instrument, and turn it on and wish you luck. We have a lot of expertise both on the irradiation side, examination side, to make sure that the research project goes smoothly, that the results are valid, and that the user has an overall very excellent experience. This is just a sampling here. A lot more expertise behind this, scientists, engineers that make the projects go well, help get things done. This slide here represents our NSUF consortium. We currently have 3 national laboratories involved: the Center for Advanced Energy Studies, we have Currently have 8 universities partnered with us and 1 industry partner, which is Westinghouse. More information on the capabilities at each one of these is available on our website. I'm going to talk a little bit now about accessing the NSUF. Our research menu includes neutron irradiation, ion irradiation, synchrotron irradiation, and of course post-irradiation examination. And these can be basically chosen a la carte. A proposal may involve only one of these, or it may involve all 4. The process for accessing the NSUF, there's some requirements behind that drive the process. The first requirement, of course, is that the proposal must be feasible, meaning that what the researcher would like to do, we're physically capable of doing. It's technically feasible. It can be done in a time frame that makes sense. That's the first driver. The second part of this is we need to determine what it's going to cost the NSUF program. We are required to fully fund all of our awards, and we obviously recognize that the applicant cannot figure this out on their own. It's a complicated process, and the applicant will need assistance from the NSUF staff. So the process is described in detail in Appendix E. I'll talk a little bit more about that in a minute. I mentioned earlier the letter of intent is a critical and mandatory first step. It's due on August 27th. It's important that applicants interested in NSUF research visit our website and contact us soon. We will need to hook each applicant up with a technical lead at each facility that they're requesting access to, so we can figure out if the proposal is going to be feasible and what it's going to cost. So your NSUF technical lead will be your new best friend for a while. Okay, this slide shows the process. This flow chart is in Appendix E of the FOA and is described in some detail. Just want to touch on a few things at the moment. The boxes across the top are the boxes that are the main FOA activities. Of course, the release of the FOA, the letter of intent, the pre-app, the full application. The boxes down below that represent the NSUF feasibility activity. You can see that that starts right up front after FOA release. It's important to contact NSUF. We will identify the appropriate technical leads. Then the process starts to really dig into the requirements associated with the request for access, to identify what the objectives of the research are, what the driving requirements are. We will capture that in a statement of work. That statement of work will be utilized to develop an execution plan and detailed cost estimates, which we will then review to make sure they're feasible, fit within the NSUF budget constraints. That can be sometimes an iterative process. That whole feasibility activity has to complete before the full applications are due, so that the value of the NSUF access and the research proposal can all be integrated and submitted when the full application is due. The boxes down the right side of this represent what happens after award. We're not going to worry too much about that today, other than mention that there is a user agreement required for NSUF access. There's a draft of that document in the FOA. I suggest you might take a look at that. Make sure your legal department is aware of that. Okay, consolidation of the work scope. So this is a big change from last year. Last year, NSUF access could be coupled to most any work scope. That created some difficulties for us during the review and the award process. So this year we have consolidated that access down to 2 work scopes. Work scope NEAT NSUF 1 has the R&D support with NSUF access. NEAT NSUF 2 is for NSUF access only, no R&D support. The NEAT NSUF 1 work scope is a work scope that's focused on any mission/program focus for a direct connection with the R&D support. When we go through those work scopes later on, you'll see there's some sub-work scope activities there that tie directly to the NE programs. The NSUF 2 work scope is a mission focus. It's a little broader work scope, provides some additional opportunities for researchers that already have R&D support.
Dan, is the letter of intent required for both NEAT NSUF 1 and NEAT NSUF 2?
Yes, the letter of intent is required for both of those work scopes. Both work scopes are requesting NSUF access.
Can any university that is not listed as a partner be granted access to NSUF?
Any university can apply for access, whether they're a partner or not. They can apply for access through the process.
Okay, good morning. I'm Brendan Heydrich from the Idaho National Laboratory. I want to talk to you about the NSUF 2 access-only work scope. This we're going to try to provide cost-free access to any of the capabilities available through the NSUF. So this, as Dan mentioned, facilities at the Idaho National Laboratory, Oak Ridge, PNNL, as well as 8 universities, and then our industry partner, Westinghouse. Same sort of projects that we're looking at for all the work scopes. Irradiation only, generally neutron irradiation in one of the test or research reactors. The larger projects, irradiation and post-irradiation examination. Post-irradiation examination only, so either you have your own samples that have been previously irradiated, or you find a sample in the sample library, that we can supply these post-irradiation examination facilities for these irradiated samples, and then the beamline experiments held at the advanced photon source. So this is, like I said, this is access-only work scope, so R&D support funding is not provided, and as Dan mentioned, you will have to provide an explanation of where your R&D funding is coming from. We don't fund travel, salaries, other user costs through this. We do fund shipping costs for the samples from the beginning to the end. And at the end, then, your samples will become part of the NSUF sample library and eventually be available to any of the researchers through the same process. We would like the preliminary development work of the samples to be nearly complete. So if this is something where you're looking at developing something and then the irradiation would only happen 2, 3, 4 years into the project, it's probably best that you apply to the R&D side only and then apply for NSUF access later in the project. Because there are both limited funding and limited access to these facilities, we'd like to keep the sort of the queue as orderly as possible. There are 4 sort of sub-work scopes under NSUF 2. The first one, core and structural materials, looking for 2 specific things this year, material degradation mechanisms due to radiation, and then also the same thing combined with irradiation and other environmental effects, whether it's a corrosive environment, a salt environment, something like that. And then also looking for testing for radiation-tolerant materials, obviously something leading toward the advanced reactor designs. Secondly, nuclear fuel behavior, both current and advanced fuel designs, looking for fundamental understanding of the behavior of these under irradiation, both to do current fuels and then to look towards the advanced fuels. Looking for radiation and thermal effects together on how that changes microstructure and the different properties of the material. And one of the things that we'll ask for all of these, but specifically for the fuels, is that the experiment is as simple as possible, certainly without being too simple, because it needs to be feasible. While we're interested in doing the best science possible, these experiments do have to be feasible to be able to complete it in a reasonable amount of time. So the tech leads will work with the experimenters to come up with a design that both satisfies their requirements, but is also able to be accomplished in a reasonable time for a reasonable budget. Third, advanced in-reactor instrumentation, and this again is split into 2 parts. So we're looking for experiments that will develop new ways to monitor experiments under irradiation. So things like dimensional changes, crack propagation, fission gas release. And then also on the power reactor side, the same type of thing, but to look to be able to do online condition monitoring for reactor vessel materials, fuel materials under irradiation. Non-traditional techniques are always encouraged so that we can build upon new technology. And then finally, any experiments with synchrotron radiation at the advanced photon source, as Dan said, advanced photon source at Argonne through Illinois Institute of Technology to the MRCAT beamline, which is one of our user facilities. They actually offer a number of techniques, X-ray diffraction, X-ray absorption, X-ray fluorescence, and then they actually have a new 5-micron spot size fluorescent microscopy system they can use. And these are basically a little bit more basic science looking at fundamental damage. Our federal program manager for this is Allison Hahn. You see her contact information here. And the technical lead is the NSUF scientific director, Rory Kennedy. So we'll pause now for any more questions on the NSUF need to.
Are fundamental studies limited to structural materials?
No, I would expect fundamental studies are available for any of the sub-work scopes.
Do I have to go through NEAT NSUF to use any available beamline at the advanced photon source?
The NSUF, the MRCAT beamline through IIT is the NSUF partner beamline. You're certainly welcome to apply through the Office of Science to the APS. It's a user facility of its own, but that would be through a different process.
Do NSUF proposals have to be coupled with an R&D proposal? Can it be coupled with last year's R&D proposal that was funded?
Well, then it wouldn't be coupled with last year's. Then you would apply to NEAT NSUF 2, which is the access only, meaning that you already have your own R&D funding. All you need now is NSUF access.
Okay, so good morning. My name is Janelle Zamore. I work in the Office of Fuel Cycle R&D. I'm also the program manager for the Transmutation Fuels program, as well as the federal point of contact on this particular work scope. I have here with me Dr. Frank Goldner, who manages the Accident Tolerant Fuel program. He's also the federal point of contact on NSUF FC 2.1, which is a bit similar to this work scope, and I'll talk about some of the differences later on in my presentation. And John Carmack from INL is our technical point of contact on this work scope. So this slide gives an overview of our Advanced Fuels program. As you can see, there are two major fuel types that we're looking at. We're looking at the accident-tolerant fuel for light water reactors, where we're trying to see how can we improve current light water reactor fuels so that we can enhance performance, safety, as well as reduce waste generation. We're also looking at transmutation fuels for fast reactors, and we define transmutation fuels as fuels that include the transuranics in addition to uranium. And we're particularly looking at plutonium and the minor actinides, neptunium and americium. And the third piece of our program is capabilities development. And this effort integrates the infrastructure and the experimental capabilities to support the two fuel types. And finally, we also have a modeling and simulation effort, which is supported by the NEAMS program. And this is particularly interesting to this work scope, as we would expect that all the data generated would be compatible with NEAMS and the Moose Bison Marmot Fuel Performance Code. Okay. This next slide gives the language for the NSUF call. I won't read everything, but we're looking for experimental data and models for advanced fuels and cladding materials that use NSUF capabilities. We're looking for separate effect experiments that link experimental data with material property data, and this will be used to validate the Moose Bison Marmot Fuel Performance Code. And some of the key items to consider, like I mentioned previously, we have an NSUF FC 2.1, which is very similar to this call. The main difference is what capability you plan to use. So if you want to use NSUF capabilities such as the advanced test reactor or hot cells, you would apply to this particular NEAT NSUF call. If you do not need to use NSUF capabilities, then you will apply to Frank's call, which is FC 2.1. And Frank is going to make a presentation on this call at 1 p.m. today. In times of constrained budgets, there's a huge difference between relevant and highly relevant. In order for your proposal to be highly relevant, you must show a relationship to elements of the Advanced Fuels program that we are currently pursuing. We're also going to give priority to light water reactor accident-tolerant fuels, as well as metal transmutation fuels for fast reactors. This last bullet gives the models and phenomenon that we are interested in. This is not a comprehensive list, but this just shows some of the critical gaps that we are trying to address. And one last thing to note is that Madeline Feltus will give a presentation later today which covers experimental data for gas reactors and sodium fast reactors. The key difference to note is that I'm looking at what happens inside of the fuel, and Madeline is looking at what happens from the fuel pin outwards. So this last slide gives the contact information for the program managers. If you have any questions regarding the program, please contact the relevant program manager on this slide. We have John Carmack from the INL, who is the technical program coordinator. We also have Steve Hayes at INL, who manages the transportation fuels program.
Janelle, can the same PI submit projects to both NEAT NSUF 1.2a and NUP FC 2.1?
Well, we would prefer that you would not do that, but if you do, you have to make sure that you delineate whether you need NSUF capabilities and you apply to this call, or if you do not need NSUF capabilities, you can apply to FC 1.2 or 2.1, sorry.
All right, good morning. My name is Richard Reister. I'm the program manager for the Light Water Reactor Sustainability Program. And so that program is focused on the existing fleet of nuclear power plants and keeping those operating as long as they can be done safely and efficiently. And so the next three work scopes are related to materials degradation, specifically for existing plants, as opposed to some of the other discussion related to advanced reactors. This is for existing plants. So the first work scope is related to targeted irradiations of light water reactor core internals. So this research would support irradiation-induced phase transformations of materials used in core internals. An example would be 316 stainless steel. Under irradiation, large concentrations of radiation-induced defects will diffuse to defect sinks, such as grain boundaries and free surfaces. This can lead to coupled diffusion with particular atoms, and this results in radiation-induced segregation of elements within the steel. So we seek proposals for irradiation of and post-irradiation examination of light water reactor sustainability core internal materials to provide validation data for phase transformation models under development within the LWRS program. So that's irradiation of core internal materials for looking at phase transformations and supporting validation of that model that's under development. That's the first one. The second one relates to gamma irradiation of light water reactor cables. So this is supports research on aging-related cable degradation. So the second one is support research on aging-related cable degradation in nuclear power plant environments. This involves the insulation material for both low and medium voltage electric cables that undergo aging. And this aging is a combination of factors such as temperature, radiation, moisture, vibration, chemical exposure, mechanical stress, and the presence of oxygen. So proposals are sought to expose cables in the high flux isotope reactor's gamma irradiation facility, followed by examinations to support the determination of remaining useful life of cables. So this would be both just the radiation effects, and you can also look at combinations of radiation effects and some of these other material degradation mechanisms, such as temperature is certainly a factor in terms of the degradation. So it's a combination of radiation and some of these other factors can be looked at as well. So that's the second materials degradation proposal, and the third. So the third materials degradation is looking at light water reactor weld materials. This will support the development of weld repair technologies for highly irradiated materials such as core internals. So again, looking at core internals, but this is for the repair of the welds in core internals. So in a collaborative program with Electric Power Research Institute, advanced welding technologies are under development for highly irradiated materials that avoid helium-induced cracking. So this welding technology involves friction stir welding and perhaps some pre and post treatment of those welds using laser heating. So these welds repairs must be resistant to long-term degradation mechanisms. So demonstration of the long-term performance of these welds is required before they can be used by industry. So we're interested in proposals for the examination of materials, both pre and post irradiation of the materials, and as well as both pre and post welding of the materials. Again, focused on essentially validating the performance of this weld repair technology and its long-term performance in the future. And those are the three materials degradation proposals in support of the existing light water reactors. Are there any questions?
Okay, we'll take questions over the next few minutes. What separate effects is the modeling group looking for ATF or LWRs?
This is Frank Grosvenor. We'll cover that in our presentation at 1 o'clock Eastern Time.
So work scopes which are not NEAT are not eligible for NSUF access?
Any proposal requesting NSUF access has to work through the NEAT NSUF 1 or the NEAT NSUF 2 work scopes. The funding that's behind those may come, for example, from fuel cycle, but the access request has to go through those two work scopes.
On the weld repairs, is this to examine an existing technique or develop a new welding technique?
The welding technique is already under development by both EPRI and actually primarily EPRI with some support from Oak Ridge National Laboratory. And so there's a welding facility that's under construction now and will be placed in a hot cell at Oak Ridge this fall. And that weld repair technology, again using friction stir welding primarily, will be welding both model materials, unirradiated materials, and then as well as irradiated materials. And so it'll be examination, re-irradiation of those materials to validate the performance of the materials after they're repaired using a technology under development by EPRI. So this is just for the examination of the repaired, well, both prior and post repair of those welds.
Hello, everybody. I'm Scott Harlow from the Office of Space and Defense Power Systems. So what I'm here to talk about today is we have a low-level development program going with NASA to develop a graphite composite fuel form for nuclear thermal propulsion. One of the issues that we have with this fuel is that it is subject to a rather harsh environment, and that being hot flowing hydrogen leads to stress corrosion. So one of the things we would like to propose is for somebody to put samples of this type of fuel into either ATR or HIFER under prototypic reactor conditions and temperatures, and instrument these non-instrumented capsules, and later on determine how the fuel performed while in a reactor. So the folks we have working on this right now are Oak Ridge National Lab, which is Luke Walls, and Jim Werner at Idaho National Lab. And the person on my team that's in charge of this is Dr. Anthony Belvin. So if you folks would help us do some sample irradiations, that would be much appreciated. So that's about where I am on that. So if you have any questions, please let me know.
Scott, can you please specify the fuel type again?
It's a coated graphite composite. It's born from the NERVA technology from the 1960s. So.
Good morning. I'm glad to present to you our call for experimental data and fission product retention and diffusion transport properties for gas-cooled and sodium-fast reactors. My name is Dr. Madeline Feltus, and I'm part of the Office of Advanced Reactor Technology within the Office of Nuclear Energy. Let me give you some motivation as to why we are going to ask for this experimental data. High quality fission product data is needed for fission product behavior, for source term effort, and we're trying to get the separate effects data we need to model TRISO fuel and gas-cooled reactor fission product dynamics, and also fission product transport within sodium fast reactor systems. The data that we need is fission product retention, temperature and time-dependent diffusion, sorption within graphite and matrix structures, for instance, radionuclide transport in predicting the fission product phenomenon, and also to get this in the sodium reactor system. I show here a picture of the diffusion constants that were available in an IAEA, International Atomic Energy Agency, technical document 978. You'll notice that this is for silver, but we also need it for other isotopes of interest. And these diffusion constants are very conservative. And the problem is that we actually have some data now from our advanced gas reactor TRISO fuel tests. So we would like to be able to bring those up to date. The other diagram on the right-hand side, our pill diagram, shows the fission product release paths for a gas-cooled reactor. Not only are we interested in what happens inside the TRISO fuel, but inside the matrix, the goo that holds the particles together, the structural graphite, the fission products that go into the coolant, as well into the confinement building. We're focused only on sodium fast gas reactors, sodium fast reactors, and gas-cooled reactors. Again, we need the fission product transfer dynamics information for microstructural and physical properties on irradiated TRISO materials, fuel matrix, and graphite during our reactor irradiation, and also during our safety heat-up tests. On the right-hand side, you will see two of our furnaces. One is at Oak Ridge, and the other is at the Idaho National Lab hot cells. We are also interested in sodium fast-cooled reactor dynamics. We have facilities at Argonne and Sandia that could be used for that work. Proposals should include experiments and data measurements. We're not interested just in computations. We would like to have separate effects tests that are focused on fission product transport mechanisms, diffusion, sorption, and retention characteristics. Particular species of radioactive materials are krypton, iodine, cesium, strontium, ruthenium, and for gas-cooled reactors, silver. So you could use non-radioactive surrogates, the chemicals themselves, and or the radioactive isotopes. We're interested in time-dependent data and temperature-dependent data. And we want these to be done at nominal operating temperatures as well as the high temperature accident conditions. For the gas-cooled reactors, we would like to have this information up to 1600 degrees Celsius. So we're seeking not only NEUP proposals, but those that are combined with the national scientific user facilities. And of course, that includes the ATR, the Advanced Test Reactor at Idaho, the Hot Cell Facility, HFEF, the Materials and Fuels Facilities, the CAES, the SEM and TEM and FIB microscopic instruments, Oak Ridge, the HIFER. The other partner reactors, you could do this at MIT or NC State. You could also have this work done at Argonne or Sandia. But we want to make sure that you do the tests. Again, we want to have sufficient separate effects tests for fission product data and or the fast reactors. So it will be your choice if you would like to concentrate on both reactor types or one or the other. Again, you can use surrogate materials at your universities. We do not want you to have a radioactive mess at your university. But we would like you to use the user facilities to use the actual radioactive isotopes. We also have irradiated materials that are well pedigreed at Idaho and also at Oak Ridge for the TRISO fuel. And we also have sodium that has radioactive contaminants at Argonne. So I show on the right-hand side the core at Idaho, hot cells, and then we have a precision gamma scanning device in the hot cells, and you would be able to use those. Proposals may use in-situ university R&D labs for the non-radioactive specimens. We want you to demonstrate your experiments and your test rig configurations so that you can show feasibility. I don't want folks sort of thinking up a test and then trying to set it up at one of the user facilities without it being demonstrated for feasibility. We also have specimens from the advanced graphite creep tests that were irradiated in Idaho, and the TRISO fuel experiments. We have DOE fast reactor experiment specimens available at our locations. The NSUF supported activities may last up to 7 years for irradiation testing, for post-irradiation evaluation, or specific sodium loop tests. And you can stagger the 3-year R&D portion at the home university because we'd like to have the students supported for the at-home work, but also to be able to go out to one of our lab facilities. Again, you can use sodium loop test rigs with non-radioactive isotopes at your home facility. But I want you to realize that you don't have to start from scratch on the sodium. I have here a regulatory technology development plan, sodium fast reactor on mechanistic source term development. It's Argonne National Laboratory. It was published this February. We can give this in the Q&As for the FOA. It's document ANL for Argonne National Lab, hyphen ART for Advanced Reactor Technologies, and it's document number 3. And again, it was published February 28, 2015. And there, please read through it. It will give you an idea of what source term work has been done for sodium fast reactors. Please look at the gap analysis and the data needs at the end of the document. It will give you a very good idea of what we're looking for and what tests we need. One of the tests we would like to have someone do is a sodium fire. I don't want to have that done at the university, of course. We have sodium burn facilities at Argonne where you could do that, or at Sandia. And again, we do have radioactive isotopes. Let me speak here about quality assurance and data retention. Proposals may have to consider doing their tests according to NQA 1 year 2009, 2008 with the 2009 accepted paragraphs. That is because we want to have data that will be used and useful and accepted by the NRC under NQA requirements. We have a method for archiving data in the Nuclear Data Management and Analysis System, MDAS, at Idaho. So as you see here, you could get the data acquisition systems and store your data. There is a firewall with the NDMAS system, but it is a SAS-based data management system. There's ways to show information and time-dependent behavior, and we can archive the data and create views. This would be very useful, especially if you're using a SAS-based environment at your home base. You can transport that and get that into NDAS, and then use that data when you're at one of the Idaho locations, or also at the other programmatic locations, Sandia, Argonne, Oak Ridge, etc., because we are interconnected. So interested universities, applicants, if you're working with vendor, please contact me. This is my information at madeline.feltus@nuclearenergy.gov. And our technical point of contact is Dr. David Petty at Idaho, and his email is shown below. Again, we could also have you contact or give you information for Argonne, etc. But please ask questions through the online system, and we'll be glad to answer your questions. Thank you very much.
Are shielding materials testing within the scope?
No. Shielding works very fine, but we're interested in fission product transport within the gas-cooled systems and within the sodium systems. Shielding walls and things like that, the fission products would typically plate out on shielding inside containment or the confinement building. So you could postulate that, but please look at the Argonne report. We also have information available at what we're looking for the diffusion and nuclide transport for the gas-cooled system as well. Shielding, fission products usually don't go through shielding materials. They just plate on. And hopefully they don't diffuse because the walls are painted with a special paint.
Do you prefer relatively small, short experiments, or do you prefer an integrated experimental plan containing various levels of experimentation?
We would like to have an experimental plan. Of course, the whole idea of having the NEUP plus this scientific user facility was to allow universities up to 7 years to have an integrated plan. If you want to put in simple experiments and have a shorter duration, that is fine. Or if you want to target them, but the funding would have to be done appropriately. So you could propose one, but we'd like to have the applicants look at a couple of isotopes, please.
Is the study of fission product diffusion in the matrix graphite material of a gas-cooled reactor fuel element part of the scope?
Yes, it is. So let me give you an example. You could take some matrix graphite, just matrix blocks themselves. We have samples of that unirradiated. You could paint one side. I'll use that. Paint it with silver, non-radioactive silver, and do a heat-up test in your furnaces at home at the university. We also have irradiated matrix material that was irradiated in the advanced graphite creep test. So we have matrix material specimens that were put in that test as well as the structural graphite. So we have that archive material. And then you could test that individually. As to having fuel particles, we don't tend to hand them out, but we do have fuel particles, loose fuel particles, and integral compacts at Idaho and Oak Ridge that are available to our applicants.
Would you be interested in molecular modeling fission product diffusion results?
If they're used to support the experimental data, but not just, ab initio, just to do it. We actually have done that for the gas-cooled reactor system, but the issue mainly is to use that sort of modeling to, let's say, derive the diffusion constants from the experiment and then validate it with molecular diffusion models. So think about using both, please.
Could you remind us where the ANL report is from, where it can be accessed on the web?
Okay, you can do it two ways. You can go to the OSTI bridge and you can search for the document. Its title is Regulatory Technology Development Plan, Sodium Fast Reactor, Mechanistic Source Term Development. The first author is David Grabaskas, Grabaskas. I'm sure if you search under Grabaskas, you will be able to find it readily. And also, it is available with the Advanced Reactor Technologies. The information is available at Argonne National Laboratories. I pulled this down from the web, from the OSTI Scientific Direct System yesterday just to be sure that it's available. But we will put that online, and of course we could possibly put the actual report up if it's possible with the NEUP community. We could do that too. So we will make sure you have the report. It's chunky. It's 150 pages, but I want you to concentrate on it so we don't propose to do what's already been done and solved. It's the gap analysis I want you to see and use.
And in the past on NEUP.gov, we've added these type of resources, links to these type of resources from NEUP.gov to their respective source.
So we can either give it to you that way or actually have the PDF online for you, so don't worry.
Are all of the facilities available to university applicants? What kind of security checks or authorizations must we obtain?
This is very good information. If you were to use K's at Idaho, that is outside the fence, so there is generally no foreign. There's a foreign access is allowed. If a graduate student or undergraduate is a foreign student, we would have to go through the standard protocol at Idaho National Lab, Oak Ridge, or Argonne. You would be set up with a specific laboratory supervisor, so we would go through that. And of course, we would like to have as many students come and work there. So again, that would be done on a case-by-case basis. We are not restricting it to U.S. citizens only. You just get to put up with the security protocols at each lab.
Could you give an example of materials where fission product diffusion rates are needed?
Yes, especially diffusion and sorption in the graphite blocks in a prismatic design. There's also graphite only on the pebble bed fuel. So we have the fuel that's packed in a sphere, and then there's graphite only regions where we would like to have that information. Let me go back to this picture. We have some SEM and TEM diffusion actual isotopes available from Caves and from the Idaho team with Dr. Isabella William. So we do have some SEM and TEM available for that. What we could do is, if there was a specific need to do a drop-in test in the Idaho test reactor, the advanced test reactor, we do have some archive material that could be irradiated for a short time. So the graphite matrix, the graphite structural graphite, is extremely important. We would also want to have diffusion and also fission product plating and liftoff in the sodium loops, and the diffusion within stagnant but heated sodium pools as well, because there is diffusion through the sodium. I hope that answered the question, but again, please look at the Argonne report. Yes, you can do a sodium fire event, but please do it. If you wanted to do it small scale at your university, okay, but we do have the facilities to do it in the sodium burn cells at Argonne, so we don't want any graduate students hurt in the process.
Those are all the questions we have.
Okay,
So
and thank you very much for your attention. And again, please contact me or Dr. David Petty should you have more questions. Or better, put it on the web and we will be answering those for you. Thank you.